Hello, and welcome to another lecture of conformal diagrams in general relativity. Today, we are going to apply what we've learned to the case of Minkowski spacetime. And so we are going to construct the conformal diagram of Minkowski spacetime. Okay, well, I don't think I need to remind you what Minkowski spacetime is, but I just write down the line element. Okay, so this is the notation we are going to use when referring to Minkowski spacetime, right? And well, you recognize the Euclidean coordinates. Okay, the thing is that for our purposes, we need to rewrite this in spherical coordinates. Okay. I don't think I need to remind you either about spherical coordinates. So I just write down the line element. Okay. And okay, so we have to find a conformal embedding of Minkowski spacetime in something bigger. Okay, how are we going to do that? Well, to do that, we are going to perform a number of coordinate transformations to this metric in order to bring it to a convenient form. Okay, so well, this is all very simple. We just have to do a number of changes. Okay, so this is the first coordinate change, which brings the metric into the following form. These are all elementary manipulations. Okay, and now, well, we have written the Lorentzian part of the metric in terms of UV coordinates, which are null coordinates, and now we are going to do a further transformation on those null coordinates, which is given by the following relation. Okay, now we go from UV coordinates to psi chi coordinates, right? And well, just another elementary manipulation. Okay. Here, it's important to notice that we're doing our coordinate transformations only on the Lorentzian part of the metric. Okay. And now, well, psi and chi are still null coordinates. We don't have terms like d psi square or d chi square. So we are going to bring this, we are going to transform these psi and chi coordinates into coordinates which are not null. And we do this transformation. Well, it's also very easy. Okay. And then, well, you have to play a bit with the properties of the trigonometric functions to obtain the final result. I'll leave you that as an exercise. Well, let me just write down an intermediate step. Okay. Plus. Okay, and so you need it's in this expression where you have to do some trigonometric transformations, which I'm not going to detail here. They are all elementary, but in order to gain familiarity with this kind of transformations, you should complete the computations yourself. I'm just going to give you the final result. And the final result is the following. Okay. Okay, just by comparing the two expressions, I think you may more or less guess what has been done in order to go from here to here. Okay, well, and now the important point is that something remarkable has happened. Okay, well, just remember that we started from Minkowski, written in simple spherical coordinates. We did a number of coordinate transformations whose details are not interested. I'm not interested now, and we ended up in something which has this form in which we see that, well, that we have managed to write Minkowski as something which is conformal to another metric. Okay, this is conformal to this metric, and the remarkable thing is that this metric is the Einstein static universe. Okay, well, I think I can just do. Well, I'm just going to write it in words. We can write formulas later. So this corresponds to the Einstein static universe. Okay, so this is the line element of the Einstein static universe. Well, I'll comment I'll comment a bit about the Einstein static universe in a moment, but the important point now is that we can rewrite this expression in the following form. Okay, just okay. So this the metric is Minkowski, so I can just write this. Okay, so well, in our convention, G mu nu, in this lecture, G mu nu is going to represent Minkowski, and now we see that we have that Minkowski is something 1 over well, I hope you don't confuse this chi with the name of the coordinate chi I used before. This is just to agree with the notation we used in the previous lecture. And this is can be written in this form, where G mu nu is now the metric of the Einstein static universe. Okay. Right. And okay, why I'm saying that we can do that? Because, well, if we can define a conformal embedding, well, just by looking at this at this expression, we realize that we can define a conformal embedding of Minkowski, of our original metric, into the Einstein static universe, and we have this function chi as the proportionality factor, which will correspond to this denominator. Why is that? Well, the thing is that we can give the explicit definition of the conformal embedding in the following way. If we agree that T prime, R prime, theta prime, and phi prime correspond to coordinates on the Einstein static universe, okay, then it turns out that the map defined in the way okay, so this is a map. Coordinates without prime are coordinates on the Minkowski spacetime, and prime coordinates are coordinates on the Einstein static universe. Then this map, just move this to the right. Okay, this map is a conformal embedding. Okay, and the reason is that reason is just given by looking at this expression. Because now if we take Einstein static universe and write it in terms of the prime coordinates, then you can, well, maybe can just, perhaps it's better if I just write it down. Okay. Okay, so this is Einstein static universe, okay? Sorry, maybe I think I need to. Now I have to add primes to the coordinates according to our convention. Okay, square. Okay, so we just write Einstein static universe in its standard form, but I'm using these prime coordinates. And so if we compute the pullback of G mu tilde by means of phi of this relation, well, okay, it's obvious that this pullback is just the expression which we have here above, but writing the coordinates without primes. Okay, so I'm just delete the primes now. Okay, and so if we compare this expression with this relation, then we conclude this relation, which proves that this map phi is a conformal embedding. Okay, so we are in a situation which was described in the previous lecture. We have a conformal embedding of Minkowski into something which, as we are going to see in a minute, can be seen as bigger than Minkowski. Or in other words, well, okay, this map is truly an embedding. So it's happening. I mean, I have just shown that this is a conformal map just by proving this relation, but now it also turns out that this map is an embedding. So we have that it's a proper subset of the Einstein static universe. Okay, and indeed we have that there is an inverse map which takes this set and takes us back into Minkowski spacetime, right? So this is all in accordance with so this is in accordance with what was explained in the first lecture. So we have a conformal embedding of Minkowski into the Einstein static universe. Well, I didn't. Well, okay. There's an issue here. I have said that there's an inverse map which does this, but I have not yet proven this. But anyway, okay. This will come in a moment, or so. Okay, so let me just okay. So we are here. So let us just, in order to see this, we need to remember the structure of Einstein static universe. Okay, so okay. Yeah. Well, what is? Well, in fact, well, it's evident from this expression. I mean, because well, since we have the explicit expression of the conformal embedding, it's clear that this relation can be inverted. Okay. So we have this relation, and well, it's obvious what the inverse of this is. The only issue here is that, well, let me just write first and speak later. Okay. Okay, so it's if this is the inverse of phi is clear, but I'm going to use a different symbol for it, I'm going to put the bar because, well, because we need to, because this is phi is acting on the whole of L. I mean, the domain of phi is L, but the image of phi is not the whole of Einstein's static universe. It's only a subset of it. So that's why I'm using here the bar. And, well, you will see in a minute why I'm saying that the image of phi is a subset of the Einstein static universe. And to see that, well, we need to follow what we explained in the first lecture, and we need to study the zero set of chi. Okay? Why? Well, because, well, if you remember from the first lecture, we said that this set is obtained by computing or what, better just to follow the notation of the first lecture. Such that okay, and well, this chi bar is obtained from chi, and the point is that, well, we are going to see that in this case this is not the empty set, because if it was the empty set, then it could happen that this inclusion would be an inequality. But since this is not the empty set, as we are going to see, we will be able to see that this is just an inclusion. Well, I think this all will become clear when we do the explicit computation. So don't worry if right now you don't quite understand it. Just let me continue a bit. So, but okay. So how do we compute chi tilde? Well, this is the composition of chi with phi bar minus 1, which we know we have that. Okay, so we have phi. So okay, and we also have the expression of chi. The expression of chi is just we just have to compare these two expressions, right? And we have to take this. We know the explicit expression of the pullback of G tilde mu nu. So we just replace this here and compare, and we realize immediately that chi is just the denominator of this quotient, and we have here the inverse of phi bar minus 1. So we do the composition and we obtain the obvious result. Okay. Okay. And so we need to find the set of zeros of this chi tilde function. Okay, so now remember the type T prime and R prime live in Einstein static universe. So this is going to be a subset of the Einstein static universe. Okay, since this expression only involves two coordinates, then we can just restrict our study to the to dimensions spanned by the plane T and R. So okay, it's easier just perhaps to draw a picture. Sorry, let me just draw the line straight. Okay, so we have this. we have this. Okay, let us assume that this is T. Right. Okay, yeah. Okay, and so, right, we need to see what this condition entails. Okay, okay, this is very easy to find. So, well, just write the result here, and well, we have actually two sets of solutions. Okay, and n prime are just integer numbers, right? Okay, so these are straight lines. Okay, I'm just going to draw this set of straight lines in the diagram. Just sorry, let me just move. Okay, I have to. Okay, just take first the diagram and then the prime later. Okay, so we have well, sorry, I just want to draw it in red. Just okay, so we have and well, okay, I just draw 4 lines, but well, you realize that there's in fact an infinite number of lines here. Okay, and well, let me just indicate which line is which. Okay. Okay. And at this point, we need to remember that the ranges of the coordinates, of the prime coordinates, because, well, if we just go back and we look at the line element of Einstein static universe, then, okay, this, well, there is a part of the line element which corresponds to the 3 sphere, so it means that the range of R prime is this, okay, because it corresponds to the polar angle, well, one of the polar angles of the 3 sphere. So it means that if we look at this this picture, we only need to we don't need to consider the whole 2 plane. We just need to consider part of it, which I am going to indicate now. Okay, well, didn't get a straight line, but well, just get a nice picture. Okay, right now we have so it means that we only have to consider the region with blue lines. Okay, right, and within this region we need to consider an open set bounded by the lines which are defined by this condition. And well, if you just look at this region, you see that there are an infinite number of open sets which satisfy this property. For example, I'm going to indicate one of those open sets with with green lines. Okay, this this open set is bounded by well, by these two lines which satisfy this condition, and well, and also this vertical line which is the boundary of the coordinate range. And but I could have chosen any of the other infinite sets which we have here, okay? And in fact, for our analysis, this couldn't have mattered. But I am just forced to pick one open set because this open set is going to correspond to the image of our. Well, let me just use the right color. This open set is going to correspond to the image of our conformal embedding. Okay, so I just have to, because otherwise, if I choose if I choose more than one open set, what happens is that the embedding, the map is no longer an embedding because we no longer have an inverse. So that's why we are forced to choose one set. And so I am just choosing this set just for simplicity, but I could have chosen any other set. And so this open set here will correspond to the image under our conformal embedding. Okay, I can just just be smaller, and yeah, I indicate it in that fashion. And well, to make things even more clear, let me just draw this open set separately. So I'm just draw again. Sorry. Okay, I draw again the diagram. Okay, but now I'm just putting only the open set which we have chosen. Okay, and well, just write the okay, and yeah, okay, and so this is now the image of our conformal embedding. And yeah, the point now is that, well, since this condition only involves two coordinates, we did the analysis in the two plane, in D prime and R prime, but okay, this is not two-dimensional. This is actually four-dimensional. So we need to think of this condition as a condition in a space of 4 dimensions, not just 2. And so these sets, which we are seeing here as sets in 2 dimensions, are actually sets in 4 dimensions. And so we need to think of them as sets in 4 dimensions. And well, this might require a bit of thinking. And but to help us, we are going to draw a representation of the Einstein static universe in 3 dimensions, because we cannot, unfortunately, I cannot write here in 4 dimensions. I have to, I can draw at most a 2-dimensional representation of something which is 3-dimensional. So I am going to draw here the standard representation of the Einstein static universe as a cylinder, which I think you're all familiar with, but I will just remind you the essential details, right? Okay. Okay, here it is. And let me just rescale this picture for you to see. Okay, right. This is the picture, right? And well, think I'm going just to put the two pictures together, because we need to work with both pictures, right? So yeah, I'm just going to take this picture and put it together with the other picture. Okay, and so yeah, we have now both pictures together. And yeah, well, I remind you, well, maybe I should just rewrite here the metric of the Einstein static universe. Okay, so this is the metric. Need a bit. Okay, I might need a bit more of space. And well, you remember. Well, I'm just doing a very brief description of the Einstein static universe. You remember that this is the round metric of S3, and so just by looking at this metric, we see that the topology of the Einstein static universe is S3 cross R, right? So this is a very brief revision of the Einstein static universe, and that's the reason of the representation as a cylinder. We have here the S3 times R, okay? And so now this, but okay, we're in this case, we don't need the whole Einstein static universe. We only need a subset of it, which corresponds to the image under our conformal embedding, right? And this image is given by the interior of this sort of triangle, right? If you remember from what was explained before. So we need to sort of take this triangle, which is a two-dimensional representation of this set, and try to figure out what this looks like in the when it's in the cylinder. Okay. Yeah. Well, we should remember that in this two-dimensional representation, each point will correspond to a circle. Well, it corresponds to a circle in the, well, it corresponds to a S2 on the 3 sphere. Well, okay, this takes a bit of thinking, but well, I think that perhaps the best is that I give you the result and then we discuss it later. So okay, so we have to put this in here, and the result when you do that is, well, is given by another picture, which, well, can be found in number of textbooks. I have, okay, so I'm just going to put it again because I need to rescale the picture. Okay, so yeah, need a bit more of rescaling. Okay, so I took this picture from the book of Hawking and Ellis, which I mentioned in the first lecture, in the introduction to these lectures. So, well, if you represent this set on the Einstein static cylinder, sorry, on the Einstein universe, what you get is this picture, where this region with the vertical lines correspond to the set we are representing. Okay, so this is just phi L. Well, this takes a bit of thinking to find out why, but well, it's clear that I'm going to just bring again this with me because I just want to have it together next to the picture of the cylinder. Okay, just right. And so, if you look at this picture, this line goes to these two lines. This is t equal to r plus pi, and these two lines below go to correspond to this. Okay. Okay, how can I cannot. I can only draw in 2 dimensions. I cannot draw in 3 dimensions. But I think that you will be able to figure out what I am saying. Okay. And then we have this vertical line which corresponds to this axis. Okay. So this okay, this is t prime. Well, this is r prime equal to 0, and this corresponds to this corresponds to r prime equal to 0. Okay. So yeah, so we have achieved a conformal embedding. Well, and now we just by looking at this by doing this analysis with these 2 pictures, we clearly see that the image is a proper subset of the Einstein static universe. It's not the image is not the whole Einstein static universe. Is just a proper subset. Okay. So we truly have, if we combine this with what I have said before, we truly see that this phi is a conformal embedding. And so we are getting a conformal embedding of the Minkowski spacetime into the Einstein universe. Okay, and we also have an explicit form of the an explicit representation of this set, okay, of the boundary, of the conformal boundary. And yeah, you see that the conformal boundary is just the, well, can be seen here as the in the 2 pictures is the union of a number of subsets t equal r plus pi equal r minus pi. Okay, and then we have a number of points as well, which are here, which are also represented here, which are what the so-called I naught, I minus, and I plus, which I also write here. Okay, well, I naught, plus, and I minus. Okay, so this is the representation. And well, the thing is that each of these regions have names. Well, I have already given the names of the points, but these sets also have names, which are the so-called future null infinity, past null infinity, and the points. Well, the name null comes because this is this. Well, if you look at the well, maybe this is better seen in the 2-dimensional diagram. These are null well, you have to bear in mind that null rays here, well, this is perhaps better seen in the, if you look at the two-dimensional part of the Einstein static universe, it's easy for you to figure out what null rays look like. And if you look here in the two-dimensional diagram, we see that null rays are just lines with a slope of 45 degrees. And since these lines have that slope, then we deduce that they correspond to null sets on the Einstein static universe. So that's why I'm saying that these are null hypersurfaces. And this is one point. And the other point is the topology of these sets. Well, perhaps the easiest is just to look at this representation. And if you look at this representation, it's and you remember that this is one of this R corresponds to one of the polar coordinates on S3, then it's easy to figure out the topology of each of the sets. Okay, so yeah. So yeah, if we define S star 3 as S3 minus the North Pole, then so it's just S3, which we have in which we have taken away the poles. Then we deduce that we deduce okay, and also we have that well, just have a look at this picture and remember that future null infinity corresponds to this line plus this line. But well, this line is just isomorphic, is just homeomorphic to the circle, but with 2 points taken away, which are I plus and this I naught, which is here. Okay. So with that in mind, it's easy to realize that future null infinity is topologically this set, and something similar happens for past null infinity. And the other sets, I naught, I plus, and I minus, are just points. Well, just look again at this picture, and you realize that they correspond to points on S3. Okay, and actually, yeah, just by looking at the values of the polar angle, you deduce that they correspond. I plus and I minus are points on the north pole of S3, and I naught is a point on the south pole. It corresponds to the south pole. Okay, so we have given a complete description of the conformal boundary of this of the conformal embedding defined by phi. Okay, but what does this description tells us about the global structure of Minkowski spacetime? Okay, let us answer to that question. And for answering to that question, we are going to look again at this two-dimensional representation, because what comes next is better seen by looking at the two-dimensional representation. Okay, so I'm going to just take again this picture and draw it here a bit bigger. Okay, so yeah, let us just clear our space and do again some pictures. Okay, so I take this. Just have. Okay. Right. And well, I'm just going to draw to indicate the points of the boundary, the regions of the boundary which we have just discussed. I plus, I minus, future null infinity. This is I naught. This is past null infinity. Okay. So, well, there's an important thing which I forgot to mention. Let me just briefly go back to the three-dimensional representation, and the point is that well, just combining the results about the topology of this set, okay, which you see, and the result which tells us what is the image of the conformal embedding, we deduce. Okay, this is not a formal proof, but it's intuitive from the picture that the closure of the image of the embedding is a compact set. Right? So what this tells us is that this embedding is it's a conformal embedding, but since the image is compact, we say that we have achieved a conformal compactification of Minkowski spacetime. Okay, and this will be true of the remaining examples which we studied in these lectures. Okay, so well, this is a conformal compactification. It's also seen here in this two-dimensional picture. Well, the picture represents a compact set, and yeah, so this is one thing which it's important. So that's the reason behind the terminology of conformal compactification. And well, it's important because we are able to represent something infinite, like a Minkowski spacetime, as something finite, which is a compact set. Okay, so here, here we have that the interior of this triangle is a representation of Minkowski spacetime. That's an important idea. Another important idea of this picture is that light rays are lines with a slope of 45 degrees. Okay, so I can just draw the congruence of light rays as well, maybe I can just do this a bit clearer, just with a thinner pen. Okay, so these are light rays which have all a slope of 45 degrees. Okay, well, let me just do the picture a bit better. Sorry. Okay. Right. Okay. I think you more or less understand what I mean. But why is that so? Well, again, this is because, well, the reason is what I explained before, is because, well, since this is a subset of the Einstein static universe, and we know that what the light rays of Einstein static universe look like, then it's just we just need to make a projection, and the result of that projection is this picture. Okay. And well, the relevance of that is that it's very easy to draw in this picture causal curves in Minkowski. Okay, so we just have to keep the curves within two light rays. Okay, so for example, I can just, this will correspond to a causal curve, and suppose that you want to study inextendable causal curves. Well, I remind you that a causal curve is inextendable if it's not a proper subset of any other causal curve. Okay, so well, this is true of, well, okay, so, well, let me just put this below, yeah, and take in I naught back. And so, for example, this is a causal curve, but it's extendable, because I can just extend it and put it as a subset of any of other causal curve. The point is that in this picture we see that there are two, well, an extendable causal curve in this picture is going to be a curve which reaches the boundary, the conformal boundary, and well, there are two possible ways to reach the conformal boundary. I can just get to future null infinity, or I can get to I plus or I minus. Okay, so if I have another curve here, I can just let it go. Well, sorry, I'm just going to use the thin pen. Can just let it go, and it can reach I plus, or it can reach I minus. By the way, this is well, if we go back to the three-dimensional representation, well, this vertical line corresponds to this vertical line. This is not part of the conformal boundary. Well, maybe this is not clear on the two-dimensional representation, but it's clear in the three-dimensional representation. Okay, so let me just solve this. This set of the, which is on the boundary of this triangle, is not part of the conformal boundary. This is important. Okay, so it makes no sense to say that and well, if we have a causal curve which ends up in this set, is not it is not inextendable, because inextendable curves in this picture must have endpoints on the conformal boundary. So if I draw this curve, I cannot say that it's an inextendable curve. Okay, so inextendable curves have to end up at the conformal boundary, which consists of future null infinity, past null infinity, I naught, or I plus and I minus. And another thing which we can see here is that, it's not possible for a causal curve to end up on I naught because the curve cannot be causal. Okay, so if I draw this, I can see that at some point the curve will become space-like. So causal curves, inextendable causal curves, cannot reach I naught. That's why I naught is called space-like infinity. It's also called space-like infinity. Okay. And since I plus and I minus can be reached by causal inextendable curves, well, indeed by time-like inextendable curves, they are called time-like future time-like infinity and past time-like infinity. Okay. In fact, there are two types of inextendable causal curves. There are those curves which reach future null infinity. Well, there are just curves whose endpoints are future or past null infinity, and there are those curves whose endpoints are at I plus or I minus. Okay, so we can distinguish two families of curves. And well, the question here might be, well, why are you taking these points as separate points? Why don't include this I plus or I minus as part of the null conformal boundary? Okay, well, maybe if we go back to the 3D representation, okay, we could have included I plus and I minus as part of the future null infinity and past null infinity. Well, okay, the answer to that question somehow can be guessed if we look at the diagram, because we see that at these 2 points the hypersurfaces which form the conformal boundary are not smooth. So somehow they must have some kind of special property, and for that reason we are keeping them as separate points, and the same is true of I naught. Okay, so that's one of the reasons why well, this is not appreciated in the two-dimensional picture, because okay, we are in the two-dimensional picture, the separation of I plus and I minus looks a bit artificial. But in the 3D picture, this separation is no longer artificial. The separation of I naught is here in this two-dimensional diagram is more natural, because here we see that this is the conformal boundary is not smooth. So yeah, so that's the point. But well, this is one of the reasons. But the other reason is that inextendable curves whose endpoints are at I plus or I minus are curves such that are curves which satisfy an interesting property, and are curves which don't have particle horizons. Okay, so what does it mean? It means the following. Take a curve such that is an inextendable causal curve, such that its endpoints on the conformal boundary are I plus and I minus. If we consider such a curve, and we compute the points such that can be influenced by the curve at any time of its history, then we come to the conclusion that those points are the whole Minkowski spacetime. Okay, so namely, we just have okay. Okay, so we have this, and then the result is that this is the result. Okay, what this I plus minus means? Well, I remind you that if you have a set, well, okay, I just want to write it. Well, maybe just one of them first. Okay, so we can join P with a time-like curve which starts at some point of gamma and ends at P. So if you look at here at this picture, you just consider this curve, okay? Consider now this curve gamma, then and just consider any point on here on Minkowski, which is, as we know, is the interior of this triangle. Then it's always possible to find a point within gamma such that, for example, this one, such that we can join this point Q with P by means of a time-like curve. Okay. Let's call it gamma prime, and this is true for any point of here of the triangle. It's easy to see that in this picture, so we come to the conclusion that for this sort of curve, well, this is the so-called chronological future. I forgot to mention this. This is the okay. So yeah, we have this interesting property also with the chronological past. Whereas if we consider a curve which has an endpoint at in future null infinity or past null infinity, this is not true. So let us just, for example, take for example, we take this curve, this curve here. Let us call it let's call it what? Let us call this curve gamma tilde. Okay, so if we compute the chronological, for example, the chronological past of this curve gamma tilde, well, it's in this picture is easy to see what this chronological past is. Well, it's just well, which color should I use? Maybe this one. Okay, so is this region? Okay, so you have to consider the set of points such that we can join those points with a time-like curve which starts at gamma tilde. Okay, with that. Well, no, it's the other way around. So we need to consider all all the points which can be joined from gamma tilde with a past time-like curve. Yeah, maybe for example, yeah, take this point p tilde, then there is a past directed time-like curve, which from a point of gamma tilde to p tilde. But if you take a point here, you cannot find a past directed time-like curve from gamma tilde to this point. There is no way of doing that. Okay. So it means that for gamma tilde we have the property that is not the whole L, and something similar happens for the chronological future. Okay, let me just sorry, I need to take some this way. So it turns out that when this happens, we say that gamma tilde, the curve gamma tilde has a particle horizon. Okay, well, maybe. Well, I'm just going to take this away, and because okay, so I'm just putting this here. Yeah, and so. Right? Okay. So and we have just came up with this property. We have shown these properties with the just by looking at the diagram. If we have tried to study those properties with the standard representation of Minkowski without using this diagram, then it could have been difficult for us to figure out these properties. And well, these are all properties dealing with curves, and well, there's another property with dealing with hypersurfaces, which suppose that I draw hypersurfaces, a space-like hypersurface sigma here. Well, suppose that I consider just this space-like hypersurface, right? Then, just by looking at the diagram, it's easy to see that any inextendable causal curve, doesn't matter where its endpoints are, will always have to meet sigma. Okay, there's no way for a curve which is inextendable and causal to of avoiding meeting sigma, because if you try to avoid meeting sigma, then what happens is that you are no longer a causal curve. You become space-like at some point, right? So that's what happens. And for that reason, we say that sigma is a Cauchy hypersurface. Okay, so by looking at the diagram, well, it's not a formal proof. I mean, what these properties which I have mentioned here are no. The diagram is not giving you a formal proof, but it's giving you a hint that a formal proof is possible. And so one of these properties is the existence of Cauchy hypersurfaces. Okay, and when we have a spacetime which has a Cauchy hypersurface, then this spacetime is called globally hyperbolic. Okay, so we have come across a bunch of interesting properties in Minkowski spacetime by means of studying its conformal compactification, its conformal diagram. Well, this picture, which is here, is called the conformal diagram of Minkowski. And since it's two-dimensional, it's also called its Penrose diagram. And well, I have illustrated in this lecture how conformal diagrams are useful to deduce a bunch of interesting properties. And well, in further lectures, we will see other examples in which conformal diagrams enable us to gain a lot of understanding about the global properties of a given space-time. And yeah, for the, another property which I have to mention regarding this picture is its shape, because at the beginning I said that we were the main idea here was to try to look at the spacetime from outside. So that's what we are doing here, and by doing that we can actually see the shape of the spacetime, and we see just here this triangle shape. In other cases, we will see that the shape is different. It's not a triangle; it's something different, and this difference will also entail differences in the global structure of the space-time. Okay, so that's all for this lecture. See you in this next lecture. Thank you very much for your attention.